Hello everybody. Welcome back to another video. Um, today I will be today today I will be reviving an old series about one of my favorite, if not my favorite, topic in mathematics. That is homotopy theory. Now 14, 15-year-old me, I don't know how old I was, wrote a bunch of notes for this series, but I never actually made videos on them. So, of course, what better time than now to continue? Today I'll be talking about cofibrations. Now, and fibrations. Now, some of you might know I made a video about the history of fibrations, which is kind of interesting. So if you want to check that out, I'll try to remember to link it somewhere where you can find it. But for today, the plan will be to go over some basic definitions. So, like, what actually is a fibration or cofibration? Talk about these mysterious objects which seem to be very important to us, i.e. mapping cylinders and mapping path spaces. And then for the second half of the talk, we will be clever, basically, and we'll construct some nice long exact sequences using the machinery that we have built up. And the long exact sequence that we'll end up with is a very useful one, which can be used, for example, in computing homotopy groups of spheres with the hop fibration. So this is very useful stuff for homotopy theory. Okay, so let's get into the definition. So a fibration, in this diagram here, it's this map P. So it's a surjection such that for any G and H, which make this diagram commute, and where I0 is this map which sends X to X0, so for any G and H which makes this diagram commute, there exists not a unique, just there exists a lift, H tilde, which makes this all of the triangles commute. And, okay, so similarly, a cofibration is defined very similarly. So, in this case, a map P, so this time our map P is over here, is said to be a cofibration if, again, for maps H and G that make this diagram commute, again, we want a map H tilde, which makes all of these triangles commute. But in this case, there's a few differences. For example, before we had X cross the interval, whereas this time we have this mapping space. And this map E0 sends a map. It sends the map zeta. So zeta, which would normally go from the interval to Y, it sends it to zeta of 0. Okay, so that's what a cofibration is. It's a map such that there exists not a unique lift, just a lift, H tilde, which will make the whole thing commute. And immediately we'll see why this is useful. Because every single continuous map, which you can think of, F, we'll call it F, can actually be factored as a homotopy equivalence followed by a fibration. So up to homotopy equivalence, every continuous map is a fibration. And dually, unsurprisingly, there's the dual notion for cofibrations. Any function can factor as, this time, a cofibration first, followed by a homotopy equivalence. So yeah, so we could say, so this is the precise statement. If we want to be a bit more vague, we could say any continuous map is a cofibration or a fibration up to homotopy. And the objects that we use to do this are the mapping cylinder and mapping path spaces. So, firstly we need to define what these are. So, let's do it. Firstly, we'll go with the mapping path space. So if you like your categories and stuff, then you can define it as this pullback the pullback of this square. But if you want to be more concrete about things, an equivalent definition is that it is the set of all pairs x, y, such that f of x is equal to y of 0. Because remember that y here is a map between I and y. Okay, so it's the set of all pairs such that f of x is equal to y of 0. Or if you like category theory, it is the pullback of this square. Okay, so that's what the mapping path space is. And we shall prove what I said a couple of slides earlier, and that is that we can essentially, up to homotopy, replace any continuous map with a fibration. So, more precisely what I mean is, if we have some f from x to y, then we can write it as a homotopy equivalence followed by a fibration. Okay, good, that's the theorem. Now, this is good, right? In homotopy theory, if fibrations, which we will see they do, if they have useful properties, this is obviously a very nice theorem to have in our locker. So, we can actually do this explicitly, which is quite funny. Normally you'd think it would be some highly theoretical proof. No, we can actually do it explicitly by just picking maps and showing that they are actually fibrations. So our homotopy equivalence here will be defined by the following map. So it will send some element of x to the pair x, and then this here, because remember, these PF, this mapping path space, is a subspace of x cross this mapping space. So this second coordinate here is just the constant path, which sends everything to f of x. So that's what that is, and I'll show shortly that this is actually a homotopy equivalence. And our fibration is going to be sending this pair to y of 1. So it doesn't care about our x coordinate really. All it does is it sends y to the end point of that path. So firstly we'll show that this is a homotopy equivalence, and then we'll show that this is a fibration. So let's get into it. Now, showing that alpha is a homotopy equivalence is not too difficult actually, because we can actually just use the projection. So remember, I'll write what alpha is up here. So alpha was our map from x to pf, which sends x to what did it send it to? Oh god. Oh yeah, x cfx, like so. Okay. Now, what we'll use is the projection. So if we do alpha first and then do the projection, well then we're just going to get x back. So that is straight up not just homotopic to the identity, that is equivalent to the identity. However, we also have that if we do the projection first and then we do alpha, that ends up being a homotopic to the identity. Why is that? Well, the homotopy we'll use is the one that sends. Okay, so remember, what do we need? We need. Okay, we'll call it HT. We need H0 to equal oh god, what am I doing? We need h0 to equal the identity and h1 to equal alpha composed with pi, to show that they are homotopic. Now, okay, what do we get? So h0, what's h0? Well, h0 will take in xy, so h0 of xy will be okay, so the first coordinate is always x. Second coordinate is y0. What's y0? Just y of s. So if y0 of s is equal to y of s, then we just get xy. So this is the identity. Good. Now what's h1? h1 of xy is equal to, okay, in this case we get, again, the first coordinate is x. Then we get y1, but what's y1? Just y of 0. What's y of 0? F of x. And if y is always mapping to f of x, then that is just the constant path. So we get what we require. So good, we've shown that alpha is a homotopy equivalence. And that wasn't too difficult. The funny business comes when we have to show that gamma is a fibration, where we have to come up with this mad function here to prove it, but we'll do it, don't worry, step by step. So let's recall the definition of a fibration first. So what we need is, for any g and h which makes the diagram commute, we need the existence of a lift h tilde which makes both of the triangles commute as well. And again, we'll do this explicitly. We won't do this theoretically, we'll do it completely explicitly. We'll define h tilde of at, because remember it takes in two inputs, to be, okay, now, what does G1 mean? Firstly, G is a map that ascends A to, remember, this mapping path space is comprised of two coordinates. So really what we've done is we've just called the first coordinate G1 of A, second G2 of A. So that's all that G1 of A is. The real craziness starts when we start talking about this J. Now, remember, J is a function. So J, oh sorry, I've made a typo here. J of AT, and then we have to evaluate it at S, is equal to the following. Firstly, when S is between 0 and 1 over 1 plus t, yes, it is equal to G2 of A evaluated at S plus st, and when S is between 1 and 1 over 1 plus t, it's equal to H of A, and the second part is S plus TS minus 1. Yep, that's right, yeah. So, let's check that this works, okay? Let's just unpack the craziness by checking that it works. So we'll go through this triangle by triangle. So firstly, let's look at this triangle here. What do we need? We need to show that H tilde of, oh, sorry guys, I'm getting a call. I was in the flow there. H tilde, okay, I0 is just A0. So what's, yeah, and this is going to be applied to S as well. No, sorry. Sorry, I lost my flow. This is equal to, okay, let's just go through it. Well, t is 0, so obviously S is going to be between 0 and 1. So what do we get? We just get, well, the first coordinate is going to be G1 of A. The second coordinate is going to be G2 of A, and then when we apply the function at S, we just get G2 of A of S. So really we're just getting G2 of A. which is obviously equal to G of A. So that's good. We got that. So the first triangle commutes. Now, how about the second triangle? Let's see. Like this one. Second triangle. Here, what do we have? We have to have that gamma of H of AT is equal to. Okay, let's just see what this is equal to. This is equal to gamma of G1 of A, J of AT. What does gamma do? Well, it just takes this thing and it applies it at 1. So this is equal to J of AT at 1. So when S is 1, well, obviously it's going to be in this range here. So so what we're going to get is H of A, and then this part here. Well, when S is 1, 1 minus 1 is just, okay, that's just 0, plus 1 times T is just T, so H of AT, as required. So indeed, gamma is a fibration. So, okay, that's great. So, gamma is a fibration, alpha is a homotopy equivalence, and so our theorem is proven. And whoever thought of this is crazy. I mean, I don't know how they thought of that, but that is some true vision right there. But yeah, okay, so obviously good. So we've shown that that is the case. So now we'll move on to the version using cofibrations. So firstly, we have to define the mapping cylinder. So again, if you like your category theory, it's the following push-out. But if you want to be more explicit, it's the following quotient. So you do Y, disjoint union with X cross I, and you, sorry, pardon me, and you quotient it by the equivalence relation where f of x is equivalent to x0. Now, let me show you what this actually looks like. Now, credit to Taylor Dupuy for this analogy, although I'm pretty sure it's quite a common one, but he's the person that I learnt it from. And that is, so we have y here, so this space is y. Well, okay, what's x cross I? X cross I is just a bunch of copies of x. So we get kind of a cylinder. And well, we're gluing the cylinder to y via f of x, because the bottom part is just, so let's say f of x is like this shape here. Let's say this is f of x. Well, the bottom part is just equivalent, so x0 is equivalent to this thing. So we've got a bunch of copies of f of x, and they're all glued to y via this f of x here. So that is a very bad drawing. Hopefully that made any sense at all. But yeah, that is what is really going on behind the scenes here with this definition. Okay, so I won't show this theorem, but I will state it, and that is the map. Okay, so let me actually tell you what this map is as well. This map is the inclusion of x, our space x, being included into the cylinder by just mapping x to the top, the very top of the cylinder. So that's what this map actually does. This x mapping to the equivalence class of x1. It's literally just including our original space to the top of the cylinder. Now, this map is a cofibration. I won't show that, unfortunately, but yes, it is a cofibration. And we have that our mapping cylinder is a homotopy equivalent to y. So that, similarly to before, any map can factor as a cofibration followed by a homotopy equivalence. Ooh, okay, good. Now we move on to fiber and cofiber sequences. And this is where the fun starts, I like to think. Okay, firstly, we'll define the homotopy cofiber. So that is our mapping cylinder, and then you quotient it out further by x cross 1, basically. You quotient it out further by x cross 1. So that's what the homotopy cofiber is. Ooh, look at this. So, okay, so if we have the inclusion of y into the homotopy cofiber, which is also cofibration, then the quotient map, which sends our homotopy cofiber into the quotient of the homotopy cofiber by y, which is also equivalent. If you look at the definition of the suspension of x, you'll see that this is just equivalent to the suspension of x. And this quotient and this inclusion gives rise to a long exact sequence of base spaces in quotation marks, which is known as a cofiber sequence. So, three maps are involved here. Firstly, we have our original map F, then we have the inclusion I, then we have the quotient map Q. And these sigmas, what they're doing is they are sending an element of the previous one, so x smash t, to f of x. So, for example, if we're going from x smash s1 to y smash s1, then this one is doing f of x, and then we're smashing it with 1 minus t. So that's what that does. And the reason we're calling it a long exact sequence is because they induce a long exact sequence of pointed sets. Oh god, sorry. Too much talking. For any based space Z, we have a long exact sequence of based spaces. So obviously this is very nice, but this is just the beginning, because it gets even nicer when we talk about fiber sequences. So again, we do it the dual notion, so we did a push out last time, so it's naturally we're going to get pullbacks this time. So explicitly what the homotopy fiber is it's a subspace of x across the path space of y. It's the settable x gamma, yamma, such that f of x is equal to a gamma of 1. Okay, good. Now, if we have the inclusion I, which goes from the loop space to our homotopy fiber, then we can do a similar sequence. Oh god, sorry. We can do a similar sequence as follows, where this time our omegas are mapping, so they're taking in a map P, and what they're doing, so they're taking a map P, and of course they're going to output another map. So omega of f at P is f composed with P, and then when you evaluate it at T, instead of evaluating f composed P at T, we evaluate it at 1 minus T. And this time, the arrows are reversed from last time, So last time we were going up. This time we're going down, which makes sense if you consider the duality between loop spaces and suspensions. And this time we get a long exact sequence like this. But the reason this is so nicer, in my opinion, is that now when z is equal to, if we let z equal to s0, suddenly we get a long exact sequence, not just of any old pointed sets, but of homotopy groups. So let's make this more precise. Firstly, note that the homotopy fiber of the inclusion is this path space of paths which begin in X but end in A. And if you look at the definition of the homotopy fiber, you'll see that's quite clear. And so applying this as before, we get we have a fiber sequence which looks like this. But now something incredible happens. When we apply this functor, pi 0, we get the following exact sequence of homotopy groups. Because recall that pi 0 of the path space of X star A is just pi 1 of X A. So, that's very good. But we can be even more clever. There's more we can do here. Look at this, check this out. Oh god, if I can survive to the end of this talk. If we have a fibration P from E to B, for some nice B, which we'll call it path connected, and if we let F be the preimage of the base point of B under P, then the inclusion of F into the homotopy fiber of F, the homotopy fiber of P, sorry, that inclusion is actually a homotopy equivalence. And what's more is that we can actually obtain a diagram, which you're seeing here, where all of the squares commute, at least up to homotopy. So 2 out of 3 of the squares commute on the nose, and one of them is up to homotopy. But, hold on a minute. Fi, this right here, like we saw before, is just this path space of paths which starts in E and ends in F. P applied to gamma is just P composed with gamma. And this is a really nice diagram because if we pass the homotopy groups, so if we applied homotopy groups everywhere, we would see that we can actually use the 5 lemma to obtain an isomorphism here, right here, between pi 1 of, well, what's this? Hold on a second. This would just be, okay, so if we're applying pi 0, we just get pi 1 of E F. What's this? Pi 0 of a loop space is just the fundamental group. So here we actually get pi 1 of B. That's just incredible stuff. And of course we can do it every single time. It's not going to be different as we go further along here. So actually we've got isomorphisms between pi n of E of this relative homotopy group and B. So now if we look up here, if this guy right here was homotopic to some pi n of, let's say, some c, we just have a long exact sequence of homotopy groups. We wouldn't even need to use relative homotopy groups. But that's exactly what we have. That's exactly what we have here because of this isomorphism. And so we have a long exact sequence of homotopy groups which looks like this. All from a fibration. All from a fibration. So we can use a fibration in order to obtain a long exact sequence of homotopy groups without even needing to go through relative homotopy groups. I mean, do I even need to tell you why this is useful? I mean, if you're a Gregorius maths watcher, long exact sequences are great. They're fantastic. And it's not just a long exact sequence, it's a long exact sequence of homotopy groups as well. So look up the hop fibration. Immediately you'll compute some homotopy groups of spheres. This right here can be used to show that pi n of S3 is equal to pi n of S2, where n is greater than or equal to 3. You can use this machinery right here. It's incredible stuff. It's beautiful. It really is. And yeah, that's where I wanted to finish. I just wanted to really hammer in how great this is. This long exact sequence. Fibrations are just great, man. They pop up in homotopy theory all over the place. I didn't really appreciate them until I was preparing to make this video. And these things pop up. I'm just waffling now. There's not going to be any more formulas or anything, but we're just going to waffle about fibrations. You might enjoy this. These fibrations pop up in spectral sequences as well. Look at the spectral sequence. Look at model categories. Model categories are highly based on the fact, where was it? It's at the start, on this fact right here, and the equivalent for cofibrations. We have homotopy equivalences, we have fibrations, we have cofibrations. Well, there you go. We have every map you could possibly imagine. So why not just generalize that? That's what Quillen said back in 1960s. He said, look, we've got any map, continuous map, can be written as a homotopy equivalence and a fibration. Well, surely, why not just say, this is not a continuous map, this is a morphism in a category, and these cofibrations are special morphisms, and these are special things. I mean, these fibrations pop up everywhere, man. Brilliant. I mean, I don't even need this conclusion right here. Wonderful stuff. And I didn't get it until literally like 2 days ago. But this is just really good. Yeah, so I'm gonna have to edit out the part where my dad called me in the middle of the video. But apart from that, yeah, and apart from the fact that I was kind of dying because I was losing my voice, but apart from that, I very much enjoyed filming this, and I will see you shortly because it's some holiday, so I have no excuses. Okay, good day. I've been waffling for ages. Ah, shit. Sugar honey, I see. No, I didn't say shit. No.